All right, hello guys, and welcome back. So I'm going to use this video. I'm going to go over the central limit theorem, or a corollary of the central limit theorem, very closely related to it, or basically part of it, you could say, and work a problem for you guys using that um, part of the central limit theorem. I like this little graphic. I pulled it off the web, and this kind of shows you some of the idea behind central limit theorem. You should have seen the video already, introducing you to it. And if you know what it basically says is that if you know any distribution's mean and standard deviation, and then secondly you take a large enough sample, then the distribution of the sample means of these different samples always give you approximately normal distribution, which is very, very powerful because it says that we can get information about any kind of mean, or finding a mean. It's very useful for statistics. So when you're trying to find what population parameters are and you actually don't know what they are, and you're using samples to estimate them, you know that your sample is going to be approximately normal. Even if you don't know what the underlying distribution is of what you're drawing from. Okay, so let's just put that in math. The equation is that the distribution of sample means is normal to the mean of the population, and now it depends here what notation you're going to use. If you're using variance in the second part here, you would take your variance and divide it by n. Now I just want to make a note because a lot of sometimes this is not used variance here, and also what we're more interested in is basically the standard deviation when we're doing our calculations and actually applying these things. So a lot of times if you're using this notation with the variance in here, you keep the standard deviation, which is what you're useful, and you just write a square here. So it is written in variance, but it's also telling you what's more important, which is the standard deviation. Okay, so a corollary of this. So let's just review quickly what this sample mean is. That if I take a sampling of a random variable x, and I take its sample size to be n samples, so I choose n x's, I just roll my dice n times, I collect all the values, I add them up, and then I'm getting an average because this is sample mean, so this is an average, and then we just have our standard average formula. Whoop, there should be a bunch of pluses here, not commas. All right. Okay. Plus, plus, plus. We're adding them all up and dividing. So it's an average. It's a sample. That's what a sample mean is. There's a corollary here, and that is the only part in this side of the expression that is basically random, as random variables, is in the numerator. And so what this distribution up here, this normal distribution, it's resulting from the sum of these random variables here on the numerator. So sometimes we're interested not in the mean itself, but in the sum up here, and that can be written. This is just some notation. So this is just notation for, in this specific context, the sum of these random variables. So x bar, or the sample mean, is the same as this sum here, divided by n. And because this is where all the random variables are in, and this is what has the distribution, we can also express this as normal. So this is a normal distribution as well. I mean, this x bar is inheriting its structure actually from this equation here, which means that the sum above has this distribution here. It's also normal, and it's just a multiple of n in magnitude. So all right, so we have another formula. This one is for the sum of a bunch of random variables. now again, so one side comment, n, the key thing to all this being okay, that this being a good approximation, is that n is sufficiently large. And well, let me just state it this way. N in practice should be greater than 30, just in practice. And that just comes from experimentation and sort of, yeah, just experimentation and approximation. This is all approximation. There's nothing exact going on here. All right, so let's use this version here. And when you're solving for sample means, it's going to be a very similar process because you're still using the normal distribution. It's just going to be a slight difference in how these n's are being treated and what the normal distribution will result in. So let's look at a problem using this. All right, so here's our experiment. We have drums labeled. They're 30-liter drums, so they're labeled that. So ideally, they're 30 liters. And they're being filled from a large vat. But of course, it's very hard to always get exactly 30 liters. In fact, impossible, right? If it's 30.000, whatever. So they're giving us more information. The amount of solution that's actually in each drum is a random variable. So let's say x is a random variable of amount of solution in a drum. And they've given us some key information right away. So they've given us the information we need to apply our knowledge of sample means. And that is that mu of x is 30.01, and the standard deviation is 0.1. Okay, so we have no equation here. I mean, no question here. But we have a thing that we can model already. We have a lot of information. So just applying right away, if I was going to apply the typical central limit theorem, I know something about the sample means of samples in this. They will be approximately, they have a normal distribution of, well, let's go ahead and put 30.01. And then here we have, well, you can write it like this, 0.1 over, well, square root of n. So I haven't given you any sample size in this. This is just about x. That's it. But just from this very limited knowledge of x, we don't actually know what the distribution of x is. That's what's key. We don't know that x is normal, but we do know that x bar is normal, and that it has, if I give you a sample size, it's going to have approximately this distribution. Okay, so that's the standard one, and then let's just apply our other version of it, our little corollary, and that is that the sum of a sample, so a sample size of n, will have n times 30.01 and n sigma squared in this specific case. This. So I've built some models about things that I would know using the information that we're given, but we haven't answered any questions, but this will be useful. And this is an important step you should take whenever you see a problem. Before there's any questions, just build the model, describe it in statistics. And that's what I've done here. So let's see what a question is and how we can use this to answer it. All right, so the probability that the total amount, what is the probability that the total amount of solution contained in 50 drums is more than 15 or 1,500 liters? Okay, so in this case, it's kind of a question about taking sample sizes of n equals 50, because we're taking 50 drums, and we're wondering about whether the probability that sum of 50 drums, so I'll write it like this using the notation from the other slide, a sum of the sample of 50, and we want to do the probability. We're wondering the probability that it's more than 1,500. Okay, so now we have 50 for n, and now we can complete that equation that we had from the other slide, and that would be that S of 50 is approximately normal to 50 times 30.01, and we can 50 times 0.1 squared. And let's just reduce those out. Those are going to be 1,500.5, and we'll get 0.5 over here. Okay, so this is our normal curve that describes the sum here, and we've used the normal curve before. We're going to calculate, actually, we're going to get a z-score first. So whenever we have the normal, remember we use the z-score, and we use this equation here. So we're interested in this value. This is our value of interest here, and we want to find out its z-score. So we're going to use this formula. You've done it many times already. And we'll take the variance. And oh, nice arithmetic here. Okay, and so be careful right here, because you have to, depending on what version of the normal notation you're going to use, the way I have it here, it's written actually in the variance. So if I want the standard deviation in my z-score, so I'm going to have to take a square root there. And when I plug that into my calculator, I get about, if I'm rounding it off, 0.71. I refer to my z table to find out the probability that z is less than that. Sorry, there's a negative here. Negative 0.71. And I get that it's approximately 0.238. Okay, be careful. Again, a little thing before you rush off to give your answer here. Our original formulation here was a question about whether it was bigger than 1,500. And when we calculate the z-score, we only got the value that's less than that, so we're going to have to take that complement to get our final value. So our probability that actually our z-score is going to be greater than negative 0.71 is equal to 1 minus this. And we get this. So approximately 76.2% probability that you have more than 1,500 liters in 50 drums.